Hi everyone, we're on to a new topic today, so we're starting with chapter 5, talking about Laplace transforms. So we're going to be trying to solve differential equations, but we're going to take a very different approach now to the one that we've taken before. Basically, the transform method is an indirect way of solving differential equations. So we have a basic idea that we're trying to implement. What we're going to do is take the differential equation that we are trying to solve and convert it into a different problem that hopefully is easier to solve, and then transform it back so that the solution of that new problem tells us the solution of the original problem. So we can think about this diagrammatically in the following way. We can start with an original problem, and we want to get to a solution to this problem. So solution to the original problem. But for whatever reason, this is challenging. We don't know exactly how to get from the problem to the solution. So we're going to take a side road here. We're going to come and turn this into a different problem. Rather than the original problem, this is going to be the problem in the transform domain. Now, the idea here, the hope, is that our transform domain problem is easier to solve than the original problem. So from there, we're going to solve and get the transform domain solution. And then hopefully we have another method for turning our transform domain solution into a solution to the original problem. So for us, this step from the original problem to the transform domain problem will be accomplished by something called the Laplace transform, which we're going to define shortly. And then we're going to get over here into the domain, the transform domain, and we're going to have to do some work. There's no way around that. We're going to have to work to get from the transform domain problem to its solution. And then to go back to the original domain, we use what's called the inverse Laplace transform. So this is the idea. We're going to apply some technique converting the given problem into something related but different, which is hopefully easier to solve. That's this step going from the original problem via the Laplace transform, whatever that is, we haven't defined it yet, to the transform domain problem. Then we solve the transform domain problem. Through some work, we get to a transform domain solution, and then we reverse the transformation process, change the solution to the transform process into the solution to the original problem, right? And then what comes after that? Well, of course, what comes after that is what can only come after that is something, and then profit. All right, so what is this Laplace transform that we are going to be looking at? Well, why? So first of all, why are we doing this? Well, it turns out that this thing called the Laplace transform that we are developing is particularly good at finding solutions to differential equations of this type. So this is a linear second-order differential equation with constant coefficients, and it's non-homogeneous, where g of t is a discontinuous function. It turns out that this kind of situation comes up a lot in mechanical and electrical systems. We've seen some methods for dealing with it, but this is an alternate approach, and it works a lot better in some particular situations. So we finally gotten to the point where we need to actually develop this machine called the Laplace transform, and here's what we do. So first we start with a function f of t that's defined on an interval from 0 to infinity. T is between 0 and infinity, including 0. And then we apply something called the Laplace transform, and we get a new thing. So what we do is we take our function f of t, multiply it by e to the minus ts, where s is a new variable, and we integrate that from 0 to infinity with respect to t. So now, since we're integrating with respect to t, all the t's are going to disappear, and only s's will be left over. And so, again, this is an improper integral because of the infinity. So technically what we're doing is we're doing the limit as t goes to infinity, and the integral from 0 to capital T. And then once we've integrated that, we take the limit And if that converges, which it won't always, but if that converges, then whatever the thing is that comes out, this f of s, is called a Laplace transform. Now, it might converge for some values of s, but not for others values of s, so we're going to have to keep track of that. For what values of s does this thing actually converge? And the other thing to notice here is that the Laplace transform is a little bit unusual because it is a thing that takes functions as an input, functions of t, and then the output is a function of s. So this notation over here on the far left-hand side is takes a little bit of getting used to. So it's L, it takes the f of t as its input, and then it is itself a function of s when all is said and done. So even though you see f of t here, the function that we're talking about is only a function of s. You should never, ever, ever see a t in the Laplace transform. And so the original domain is in terms of t, the transform domain is in terms of s. S is this new introduced variable. All right, let's take a look at this thing in action. Let's find the Laplace transform of a few basic kinds of functions. So the first function we'll try to find the Laplace transform of is an exponential function, so e to the at. Here we have the definition, just applied to e to the at. So again, we take our function, e to the at, always multiply by e to the minus st, and then integrate from 0 to infinity with respect to t. So this improper integral can be properly written out as the limit as capital T goes to infinity, integral from 0 to t. And then I'm combining my exponents together here, e to the minus s minus a times t dt. All right, so let's calculate. We have to take this in two different ways. So if the variable a, if the value of s is equal to a, then this whole thing here will be 0, and we have to integrate in one way because this is a constant function. However, if s is not equal to a, then this is an exponential, and we integrate according to that rule. So we're going to have to take those two cases separately. So first of all, if s is equal to a, then our Laplace transform of e to the at a, because s is equal to a, is equal to the integral from 0 to infinity of e to the 0 dt. So that's the integral from 0 to infinity of 1 dt. Now writing that out properly, that's the limit as t goes to infinity of, well, our antiderivative here is t, and we integrate that from 0 to t. So plugging in, that's the limit as capital T goes to infinity of t minus 0. And that, of course, is infinity. It diverges. So for s equals a, we conclude that the Laplace transform does not exist. That's a little bit discouraging. Oh well, let's continue on. Let's look at a case now. What if s is greater than a? Well, now it's going to be a little bit different. Our Laplace transform, got a little carried away with my cursive there. Let's try it all over again. My Laplace transform of e to the at of s is equal to, I'm going to write this in its proper form right at the beginning. The limit as t goes to infinity, integral from 0 to t of e to the minus s minus a t dt. All right, so we need to take an antiderivative. That's easy enough to do. Remember that this entire part out front here, the minus s minus a, this is all a constant with respect to our variable of integration, which is t. So here we get our function is minus, our antiderivative is minus 1 over s minus a e to the minus s minus a t from 0 to t, and we're taking the limit still as capital T goes to infinity. All right, sorry, got a bit scrunched up there. Hopefully you can read what we've got. So now we need to plug in our capital T there and our 0. In fact, let's just make those a little bit easier to read by changing the color. So that's from 0 to t. Okay, so now we get what? This is the limit as t goes to infinity of plugging in the capital T minus 1 over s minus a e to the minus s minus a t plus, because minus minus, 1 over s minus a. Now, considering what we have here, remember s minus a, s is greater than a, so this is positive, negative sign there, and we're taking the limit as capital T goes to infinity. So this entire exponential form here should go to 0, does go to 0. So this is all 0. The second part over here, the 1 over s minus a, doesn't have any capital T's in it, so we just get that constant. So 1, let's try that again, 1 over s minus a. All right, so our Laplace transform is often denoted by a capital letter with s as its variable. That's the Laplace transform of e to the at, as a function of s, is equal to 1 over s minus a for s greater than a. That is the Laplace transform. So that's our first Laplace transform that we've calculated. It doesn't exist when s equals a, but for s greater than a, it does exist. If you try to do this with s less than a, what you'll find is that it again diverges because our exponents here are going to have positive coefficients. And so as t goes to infinity, the whole thing will diverge. All right, so that's the Laplace transform. We're going to remember that one for later. We'll come back to it. We're going to want to list all of the ones that we find eventually. We're going to have a big table of them. That's coming up. All right, let's try one more. See if we can put this into practice again. So this time, let's take the function f of t equals t. Pretty straightforward. We should be able to do this. So by definition, the Laplace transform of t, function of s, is equal to the integral from 0 to infinity of t times e to the minus st dt. Right, again, you take your function times e to the minus st. And we're going to have to calculate this integral and then take the limit. In order to do the antiderivative here, we're going to need to use integration by parts. So we'll do that as we get to it. All right, so the Laplace transform of t of s is equal to, well, let's back up a little bit. Let's just do the integral first, and then we'll come back and take the limit, and that'll be our Laplace transform. So we're going to do the integral from 0 to capital T of t e to the minus st dt. Now this is going to be by integration by parts, so I need a u and a dv. My dv, well, let's start with my u. U will be equal to t, so du is dt, and my dv is everything else, so e to the minus st dt. So v, its antiderivative, is minus 1 over s e to the minus st. All right, so that kind of gets sequestered away down there. Now when we plug it in, so we have u times v, so minus 1 over s t e to the minus st. Now we have to remember, though, that this is a definite integral. So this goes from 0 to t. We have to evaluate it at the endpoints. Minus the integral from 0 to t of, now it's v du. So minus 1 over s e to the minus st dt. Great. So plugging things in, we have that this is equal to, plugging in my t's, I get minus t over s e to the minus st, capital T, okay, plus 0, right? It's going to be 0 here for the t. Minus, now I'm taking the antiderivative over here, I get minus, or positive 1 over s squared, because I'm going to divide by minus s again, e to the minus st, and that goes from 0 to t. All right, so up front here, we have minus t over s e to the st plus well, minus, plus, minus, minus, let's get that right, minus 1 over s squared e to the minus s capital T minus 1 over s squared. All right, and now finally we need to take the limit as t goes to infinity. And what's going to happen there? Here we have, at the first part, we have t over e to the st. If s is positive, this whole part will go to 0. If s is negative, then this thing will diverge. So we have to consider only s greater than 0 for this to work out. In any case, if we have that, then our whole first part here will go to 0. Similarly, this part here, because we have e to the minus st times a constant, this will also go to 0. And so what we're left with is that the Laplace transform of t of s is equal to positive 1 over s squared for s greater than 0. Right? So we're going to remember that. We went from t to 1 over s squared, s greater than 0. All right. Lastly, let's look at one more example. In this case, we want to know, what about the Laplace transform of e to the t squared? Now, we apply the same formula. We have the integral from 0 to infinity of e to the t squared times e to the minus st dt. And if we put that together, we can rewrite it as, again, we do the proper integral. Limit as t goes to infinity, 0 to t. And now it's e to the t times t minus s. Now, it doesn't matter what value of s we pick, no matter how large or small we choose this value of s, this exponent in the top is going to be positive for large t. So this function, e to the ts, or e to the t times t minus s, goes to infinity, right? The integrand will go to infinity, and that means that the area under that integral will also go to infinity. So this entire thing will diverge. This improper integral will never converge no matter what value of s we pick, so the Laplace transform of e to the t squared does not exist for any value of s. It just doesn't exist. So there's something that can go wrong with a function that seems pretty nice, right? E to the t squared, not so bad. It's just an exponential with a polynomial in there, but somehow this doesn't qualify for this Laplace transform thing that we're trying to do. To figure out why that is, we need to do a little bit of theory, and that's going to be the topic of the next video that's posted. So tune